Since we will often have to do with these delay distributions in our discrete event simulators, let me give you a general introduction to the topic. This is a bit of a fast introduction. You will learn much more in a statistics class, but it will do for our purposes. So imagine that you have a memoryless process. What I mean is this. Imagine that you have some quantity of something, and imagine that every unit of time that passes, half of it goes up in smoke, goes poof. And the probability that something stays or goes up in smoke is not related to how long the thing has lasted so far. This is what is meant by memoryless, right? Every time unit, everything has an independent probability of continuing to existing or stopping that does not depend on the past. So what will happen? Well, originally you may have a quantity 1 of something. Then the next time instant you will only have 1/2 of it, of course. Then the next time only 1/4 of it, and so on and so forth. Okay, so this will follow a decay process. So this is called a memoryless process, because the probability that something decays is not related to how long it has lived. Atomic nuclei behave in this way when they undergo radioactive decay, right? A certain percentage of them decays every time unit, and the probability that a nucleus decays is not related to how long it has existed, okay? So if you have a memoryless process, the quantity of stuff that you have remaining after time t is given by e to the minus alpha t, where alpha is the decay constant, okay? You can see that this models a memoryless process because suppose you are at e at minus alpha t is the quantity after t. What is the quantity after t plus 1? Well, it's simply e to the minus alpha t plus 1. So it is equal to the e to the minus alpha t times e to the minus alpha. So e to the minus alpha is essentially how much the quantity decays in one time unit. Okay? You can also verify that if you take 2 times t1 and t2, okay, that the amount of decay between t1 and t2 is only related to the distance from t1 and t2 and not from the distance from the origin. This is essentially a restatement of the memoryless property, right? The amount of decay depends on the distance in time, but not on how long things have been alive. And you can do the calculation if you don't trust me. The ratios between these two quantities is equal to so e to the minus alpha t1 divided by e to the minus alpha t2. And so this is e to the minus alpha, t1 minus t2. Or if you prefer, e to the alpha t2 minus t1. So, because t2 minus t1 is positive for a figure. Okay, so you can see that the quantity of decay, the ratio between the two quantities, only depends on the distance between t2 and t1. Okay, so this is a memoryless process, and in particular, what is the instantaneous probability of decaying at time t? Well, we can reason like this. The quantity, as I mentioned, is given by e to the minus alpha t. So what is the instantaneous probability of decay? Probability of decaying at time t is equal, call this the quantity at time t, okay? Is equal to minus the derivative of the quantity at time t, right? Because the probability is equal to the decrease rate of the quantity. And so if you do the calculation, this is equal to minus the derivative of that, which is minus alpha e to the minus alpha t. And so this is equal to alpha e to the minus alpha t. Okay? So the instantaneous probability of decay is equal to alpha e to the minus alpha t. Now, the other thing you may wonder is, what is the average life? What is the mean of this distribution? This curve of P of t, by the way, is again, it again looks like an exponential, except it has this scale factor alpha in front of it. What is the average of such a distribution? So the mean or average is given by the integral between 0 and infinity of t times P of t in dt. And this is equal to the integral between 0 and infinity of t alpha e to the minus alpha t in dt. Okay? And it turns out that this thing is actually equal to 1 over alpha. So this is the mean of the distribution. So this sort of makes sense. Alpha is the decay rate, and the higher the decay rate, the smaller the mean. Good. So these are memoryless processes that generate exponential distributions. Now, your question is, why do we care? We care for the following reason. Imagine we are modeling the following system. Here is a supermarket, big building somewhere. And here are all the people that may be interested in going shopping. So here is one, here is another one, here is another one, here is another one, and so on and so forth. Okay, and every one of them is in their own homes. And so these people, mostly don't know each other. And at some point they feel hungry, open the fridge, check it out, and say, well, it's empty. And so they decide to drive to the supermarket, okay? And if we model the supermarket, we want to model it as a sort of process that sort of generates one person at not at regular intervals, at random intervals, and sends it into the supermarket. And our question is, how much should we wait between generating one customer and the next? How should the time between customers be distributed? In particular, imagine that I want to draw this particular line. So this is time, and this is a probability, and here is 1. And I want to know, so this probability is the probability that there is at least that much time before the next customer. So at least this much time before the next customer, okay? From one customer to the next customer. And so this line somehow, will have some shape that will go down. So it will not have this shape, in fact. It will have a shape that goes monotonously down in some way. And we wonder, what's this shape? How is this distribution shaped? Okay? And so think at it like this. To figure out the shape of this distribution, let me reason as follows. Take these to be now. So, this is a time in which I am now. And consider several hypothetical situations, or several hypothetical supermarkets, or these conditions. One is the one in which the previous customers entered at this point in time here. In another case, the previous customer could have entered here quite a bit before, right? In yet another case, it could have been quite recent. Okay? So these are the times in the past. Now the time again goes in the future in this way. So these are the times in the past when the prior customer arrived. And we are now wondering, how long do we have to wait until the next customer? Okay? So in other words, the time till the last customer has already lasted, if you want to look at it this way, which is a useful way to look at it. No? The time since the last customer has already lasted this long, or this long, or this long. And we are wondering, how much longer will it last? Well, we don't know, but we can reason as follows. Imagine one of these squares is 1 minute. Okay, not a super popular supermarket, I guess, but... So, in the next minute, there is a certain probability that a new customer shows up. If it does show up, it will break, by showing up, the continuity of these past intervals of time. In this case, it was 2 minutes without a customer, and now, there is a new customer. In this other case, it was 4 minutes without a customer. In this case, only 1. But if this red customer arrives, it interrupts all those periods without customers, okay? And the red customer does not know the previous customer. His probability or her probability of arrival is completely uncorrelated from the time at which the prior customer arrived, because these people don't know and don't care about each other. So the probability of interrupting a 2-minute customerless sequence is the same probability of interrupting a 4-minute customerless sequence, and is the same probability of interrupting a 1-minute customerless sequence, okay? So let's call P this probability of interruption. Well, I should draw it in red, really. Let me do that. Just 1 second, okay? It is like the red person. So I have this probability. P is the probability of interruption of if you want, of customer in the next minute. Minute. So this is great. And then if I call things this way, then 1 minus P is the probability that the customerless period lasts 1 more minute. Okay? And so, think at what is the distribution of this incognito distribution above. How does it have to look like? Well, it needs to look something like this. Now, here is time, here is 1. You have a 0-minute customerless sequence with probability 1, because that's, no time, nobody has time to arrive. Then, if this is 1 minute, imagine we measure time by minutes, 1, 2, 3 minutes, okay? Then, the probability that it will last 1 minute is equal to the probability that you are not interrupted, which is 1 minus P, okay? The probability that you last 2 minutes is 1 minus P times 1 minus P. No? Because you have to have survived the first minute without interruptions and the second minute without interruptions too. For 3 minutes, well, you get the hang of it, I guess, right? Is 1 minus P cube. Okay? So this is in general an exponential distribution. Okay, I drew the integer points. But this is an exponential distribution. So this is why it's called memoryless. If things happen without memory of the past, the inter-arrival times, the times between events are distributed according to an exponential distribution. Okay? And so we can say in general that this cumulative distribution P of t is equal to prob of no customers for at least t, is equal to e to the minus alpha t, where alpha is the parameter, as we have already seen, of the exponential distribution. Good. We will be using another distribution often. So imagine that you need a certain number of things to happen. For example, you need to wait for 3 customers to arrive. This is, customer 1, if you will, and this is the event of it arriving. This is the event of customer 2, and then, customer 3. So imagine that you need to wait for the arrival of k of them. In this case, k is equal to 3, okay? But imagine that you need k of them, and the arrivals are distributed according to e to the minus alpha t, okay? So it's an exponential distribution of parameter alpha, okay? And you ask, what is the distribution of the total time? So how long does it take you to do or to witness 3 events, each one of which is distributed in a memoryless way? And the answer is a gamma distribution that has parameters kappa and alpha, or k and alpha. And the gamma distribution, you look up the formula on Wikipedia, has a somewhat complicated formula. But it has very beautiful properties. One of the properties for us computer scientists is that if you need numbers distributed in this way, if you need to pick out a random number that is distributed according to this, time it would take for a group of 3 people to arrive, you can just do np random gamma of k and alpha, and out pops a number with the appropriate distribution. So this is very convenient. It's a classical distribution and is very handy. But now I want to tell you why it is so incredibly popular. Okay, why you will find it, we Italian would say, a little bit like parsley, because we use parsley in many recipes. And so when you least expect it, gamma distributions pop out. How comes? Well, so there is a reason why things are distributed in a bell shape, and in fact often with a Gaussian distribution. There is this fundamental theorem of statistics that says, if you sum a lot of random variables, even if the random variables have a funny distribution, they can be uniformly distributed between 0 and 1, so every random variable can have a distribution like this, or a distribution like this, or be a sort of misshaped distribution. It doesn't matter, but if you sum a large number of random things, the total will assume a Gaussian distribution. Okay, this is one of the most fundamental results in statistics. And if you are a little bit patient, I want to tell you in the end why this result was also important for the for genetics. Okay, but bear with me a second. So these sort of bell curves or distributions that have one lump are very common. And people wish to use them in many phenomena. When you get data out of an experiment, it's quite common to assume that it's distributed in Gaussian way. Because if your data is the result of a lot of small effects, it just stands to reason that the distribution of your data should be roughly Gaussian, that's why when you make a measurement and there is a bit of noise, since the noise is the sum of many various reasons why you may be doing it wrong, the distribution of the measurement will be roughly Gaussian, okay? Now, so suppose we have to model a phenomenon, like as we will do in the next lesson, how long it will take for the bus to go from one stop to the next, okay? So we would like to do something like this, okay? This is time, okay, this is 0 time, and I want the probability that the bus takes a certain amount of time to go from one stop to the next. Now, maybe the stops are somewhat regularly spaced, and so if this is, I don't know what it is, but 3 minutes, okay, I will assume that it will be like a bell shape around 3 minutes of some kind. Now, I haven't told you why gamma distributions are popular, but here we come to it finally. So if this was a Gaussian distributions never go to 0 as you go away from their middle, from their hump. Okay? They go very close to 0, but they never quite reach 0. No? So even if you look at, for instance, 6 minutes, this is not going to be 0. It's going to be super small but non-zero. And this is fine, sometimes there are big traffic jams, I guess. what's not really fine is that the Gaussian distribution would also be non-zero. Sorry, this is a really bad line, but would also be non-zero when you go to negative time. And this makes no sense, because you cannot have a positive probability, even though small, that the bus actually arrives before it departs, right? This doesn't work. So we want to use a distribution that looks kind of like a Gaussian, but has this guarantee that in negative time it's actually going to be zero. Okay? What is this distribution? And the answer is the gamma distribution. The gamma distribution works in this way, gamma. And again, look at Wikipedia. It has beautiful diagrams. I wonder why teachers generally don't like Wikipedia. I used to work with Wikipedia a lot and I'm a fan. There. Okay. The gamma distribution looks like this. Remember, it's a gamma that has two parameters, k and alpha. K means how many things you have to do. Alpha is the speed of each thing. So, if you need to do only one thing, then this is just the memoryless distribution we saw before, okay? So here is one, I guess, and so it's just like, a beautiful exponential. So, not lumpy at all, and not very useful, but okay, fine. Now, if you move to, so this blue line is for k equals 1. Now, if you move to k equals 2, the curve starts to be like this, What's the probability that to do two things it takes time 0? Well, it's actually this is not 1. Sorry, let me erase my mistake. Because this is a probability of something happening at a given time. So, if you need for two things to complete one after the other, the probability will actually look like something like this, So this is a curve for k equals 2. If you move on to k equals 3, okay, the curve will be, I want to follow my finger, no? It will be something like this. So this is k equals 3. And if you allow me to zoom immediately to a much higher value of k, this is again where the central limit theorem of statistics applies. So if you sum a lot of things, let me draw it in, violet. So for k that is equal to, say, 20, the curve will be very peaky and very similar to a Gaussian. In fact, the greater the k, the more similar to a Gaussian. That's the central limit theorem. Okay? But the gamma distribution is not a Gaussian. It has this absolute guarantee that it is 0 for k greater than 1 at time 0. And that anyway, the guarantee you want is that it's 0 for negative times. So you can just integrate it from 0 to infinity, and this integral is going to be equal to 1, okay? So you don't lose the probability to this silly case of things happening before 0 time. And so the gamma distribution, you will see it a lot in the modeling of stochastic systems or random processes, because it's essentially the generalization of a Gaussian to the case in which things cannot go in negative time. So the Gaussian is used very often for things that add up and can have both positive and negative values. The gamma distribution is the most common distribution for things that, have to have a humpy shape but cannot be negative. And now, if you bear with me for a second, I just want to tell you a fun fact between the interaction of Gaussian curves and genetics. Genetics started with Mendel, who discovered, that peas can be either smooth or wrinkly, right? And their offsprings, if you mix them in a certain proportion that is fixed, would be either smooth or wrinkly. And the proportion depended, on which kind of hybrids you mixed how. But essentially, each pea had two genes, a smooth and a wrinkly one. Sort of, let me draw the wrinkly one like this, the wrinkly gene. And so, you had the three possible situations, two smooth genes, a smooth and a wrinkly, and two wrinkly genes. And there would be two outcomes of exterior aspect. This would be smooth, this would be wrinkly, and these, well, I have to admit, I don't know. It goes either one way or the other, and I forgot which one, but it's not important for the discussion. You can look it up on Wikipedia, of course. But so this was at the beginning of studies in genetics. There were two theories about how an animal would get its adult form. One was through the genes, and the other one was through effects in womb and later. And not only, but the idea was that the animal was able to inherit some of the aspects of the parent. So it was not generated by the genes at which it was born, but the situation of the parent when it was born, right? So acquired characteristics by the parent could be inherited by the child. This was some of the opposing line of thought. And the geneticists were saying, no, look, it depends on the genes. And the common retort at the origin of genetics was the following. Well, look at humans. Okay, so if we look at the distribution of height of a human, the height of a human is distributed according to a sort of Gaussian, okay, in which there is a most common height, then there is, well, again, this may be a gamma distribution, in fact, but you know, humans also taper off after some number of feet. You know, I don't think there has ever been a 9-foot human. But, you know, there was some, like, the laws of physics after some point, you know, make some body architectures impracticable. But essentially it's a lumpy curve of some kind, the one of height, right? So this is the height of a human, and this is a probability of having a certain height, and this is a height. And so the people that opposed the genetics were saying, look, if you really had a gene for height, this is not at all how it should look like, right? The way it should look like if you had a gene for height is that, well, you should have, you know, some shorties and then some tallies, and that would be it, right? Because, you know, there is a gene, and either the gene is flipped in one way and then you have a shorty, and this flipped in another way and you have a tolly. But there shouldn't be like this bell curve at all, right? It's a discrete phenomenon. I mean, if you measure the rugosity of a pea, you don't get, you know, that like rugosity and probability. You don't get a bell curve, not at all. You get, you know, the smoothies over the wrinklies, and so we should have the tallies and the shorties here. And why don't we? And this was solved in part, this problem, by an advancement of statistics, namely by the central limit theorem that I was telling you before. The sum of a large number of independently distributed factors tends to have a Gaussian distribution. So if you assume that your height is not dependent on a single gene, assume that there is a bunch of genes, maybe 100, maybe 200, all of which have a slight influence about your height, because there is no gene that cares about your height, perhaps. Maybe there is a gene that says, you know, your liver will work in this way and that way. And another gene would say, oh, your bones will have, you know, tend to have this density rather than that. And another gene that says, oh, your cartilagen and yada yada, no? Oh, the head shape and whatever else. Oh, the, you know, and so all these things put together, your height is the sum of a very large number of factors, and hence it's Gaussian distributed. So it is interesting to me that there is a connection ultimately between the development of genetics, statistics, and the central limit theorem of how Gaussians arise, and the gamma distributions that we will be using in our simulations in order to model physical phenomena. Thank you.